Thank you very much for the introduction. I would like to talk about big data challenges for data analytics. I do not talk about smart cities, even though some believe that smart cities urgently need data analytics in order to make useful and important research. We have been dealing with increasing amounts of data and often high velocity data for some time. Some of this big data is new, such as data generated from smartphones or sensors. Much of it is unstructured. A growing number of social media and mobile technologies are generating geospatial and time data, and many data sources operate in real time. To make statistical claims about the data set, we need to know where the data come from. It is similarly important to know and account for the weaknesses in the data. Researchers must be able to account for the biases in the interpretation of the data. Without these biases and limitations being understood and outlined, misinterpretation is the result in reality. What is data analytics? Data analytics addresses problems. Big data poses to statistics, the science of how to analyze and draw conclusions from data. Research on data analytics is a new discipline that has emerged to the need for professionals in the industry and researchers in academia to deal with massive data. The scientific community and the defense enterprise have long been leaders in generating using large data sets. More recently, the emergence of e-commerce and massive search engines has led other sectors to confront the challenges of big data. Examples include Google, Microsoft social media such as Facebook, YouTube, Twitter, or Alibaba in China. Having data measured in exabytes, this means 10 to the power 18 bytes. And it is important to realize that data mining of this big data is transforming how we think about data storage and retrieval. To the extent that big data can be exploited effectively, the hope is that science will extend its reach and technology will become more adaptive, personalized, and robust. Very large-scale data sets introduce many data management challenges. Two notable ones are managing the complexity of the data and harnessing the computational power required to ingest and analyze the data. Managing the massive amount of data is one of the most apparent technical challenges in big data analytics. In some cases, it may not be a viable option to store data. This can be either because it is physically and/or economically infeasible to store immensely large volumes of data, or that the management overhead becomes too large. For example, when data is updated faster than it can be stored. Streaming processing is an approach to addressing several of the challenges concerning analysis of the data that cannot be, may not be, or is better not to store. Combining data from multiple sources is another challenge, especially if this data comes in very different forms, such as sensor readings in design documents. Transport and smart cities is a prime example of the need for combining from multiple sources, while at the same time taking care to preserve privacy. Tools for analyzing massive data must be developed with an understanding of the developing capabilities of massive data. Scalability is one of the most crucial technical challenges of big data analytics. Current methodologies will only scale to certain levels of complexity and amounts of data. Beyond such levels, current methodologies will become increasingly irrelevant and likely not to be suited for providing refinements in analysis of competitive value. But several decades of R&D in databases and search engines have yielded a wealth of experience in the design of scalable data-centric technology. In particular, these fields have fueled the advent of cloud computing and other parallel and distributed platforms, such as, for example, the Hadoop file system that seem well suited to big data analysis in general. Nevertheless, it is extremely difficult to develop parallel distributed programs. Furthermore, innovations in the fields of machine learning, data mining statistics, and the theory of algorithms have yielded data analysis procedures that can be applied to ever larger data sets. However, such optimism must be tempered by an understanding of the major difficulties that arise in attempting to achieve the envisioned goals of big data analysis. It is worth noting that the challenges of big data go beyond the storage, indexing, and querying that have been the province of classical database management systems and classical search engines, and instead hinge on the ambitious goal of inference. What is inference? Inference is the problem of turning data into knowledge, where knowledge is often expressed in terms of variables not present in the data per se, but in models used to interpret the data. Statistical rigor, rather than belief, is needed to justify the inferential leap from data to knowledge. And many challenges arise in attempting to bring statistical principles to bear on big data. There are many issues impinging on the quality of inference. One major issue is that of sampling bias. This issue seems to be especially severe in big data sets, which often consist of many sub-collections of data, each collected according to a particular choice criterion and with little control over the overall composition. In a large system involving interconnected inferences, it can be difficult to avoid circularity, which can introduce additional biases and can amplify noise. Assertions of knowledge require control over errors, and a major part of the challenge of big data analysis is that of developing statistical, well-founded procedures that provide control over errors in the setting of big data. In science, the goal is often to find unusual or rare phenomena, and evidence for such phenomena may be weak, especially when one considers the increase of error rates associated with searching over large classes of hypotheses. Other sources of error include the high-dimensional nature of many datasets, lossy compression of data, issues of heterogeneity of the data, biases arising from uncontrolled sampling patterns, and unknown failures in algorithm creation. In general, data analysis is based on assumptions, and the assumptions underlying many classical data analysis methods, such as, for example, sessionarity and independence, are likely to be not met in big data sets. Data analysis can deliver inferred data at a certain level of quality, and there must be explicit consideration about it. It is needed to add error bars to the inferred analytics. This point of view is missing in much of the machine learning literature up to now. While there are many sources of data that currently fueling the rapid growth in data volume, a few forms of data create particularly interesting challenges. First, much current data involves human language and speech, and increasingly the goal is to extract aspects of semantic meaning underlying the data. Examples include sentiment analysis and the full-blown semantic analysis required by question answering systems. Second, video and image data are increasingly prevalent, creating a range of challenges in large-scale compression, image processing, computational vision, and semantic analysis. Third, data are increasingly labeled with geospatial and temporal tags, creating challenges in both maintaining coherence across spatial scales and time and in data analysis. Fourth, many data sets involve networks and graphs with inferential questions hinging on semantic notions such as centrality and influence. The deeper analysis required by data sources such as these involve difficult and unsolved problems in artificial intelligence and the mathematical sciences that go beyond issues of scaling existing algorithms. Harnessing big data to support causal inference represents a central scientific challenge. Key applications areas include climate change, healthcare, comparative effectiveness, and behavioral economics. Massive data open up exciting new possibilities, but present daunting challenges. The literature on causal modeling has expanded greatly in recent years, but causal modeling in massive data has attracted only very little attention so far. Building effective models for the analysis of massive data requires different considerations than building models for small data sets that have been more common in traditional statistics. Having access to much more data may open the door to alternative approaches. For example, are missing data less of an issue because we have so much data that we can afford to lose some of the observations? While the answer is probably no to this question, it may well be that better strategies can be developed to deal with missing data. The literature currently frames model selection around a bias-variance trade-off. Is this still relevant for massive data? Is variance still an issue? In some cases, when there are many variables per observation, it will be. But in cases for which the number of observations is larger than the number of variables, the issue is less clear. Finally, with massive data, large N and possibly large P, it may be easy to find many statistically significant results and effects. Whether these findings have substantive relevance, however, becomes an important question, and statistically significant correlations and effects must be evaluated with subject matter knowledge and experience. Challenges also exist in better visualizing big data sets. While there have been advances in visualizing data through various approaches, most notably GIS-based capabilities, better methods are required to analyze massive data, especially data sets that are heterogeneous in nature. One appealing approach is to support massive information visualization by way of specialized hardware, namely by graphics processing units. While inference is increasingly used to power data products that are generated by machines, there is also a need to develop tools for bringing humans in the data analysis loop at all stages, because knowledge is often context dependent, and there are aspects of human knowledge that for the foreseeable future are beyond the capability of machines. More specifically considered, many data sets require semantic understanding that is currently beyond the reach of algorithmic approaches and for which human input is required. Human input may be obtained from the data analyst throughout the data analysis pipeline. It may also be obtained from crowdsourcing, a potentially powerful source of inputs that must be used with great care, given the many kinds of errors and biases that can arise. So let me come to the closing remarks. First, big data analysis is not the province of any one field, but rather an interdisciplinary enterprise, or I would say a transdisciplinary enterprise. Second, solutions of big data problems will require an intimate blending of ideas from computer science and statistics. Third, essential contributions are also required from applied and pure mathematics, from optimization theory, and from various engineering areas, notably signal processing and information theory. Finally, domain scientists and users of technology also need to be engaged throughout the process of designing systems for big data analysis. Thank you very much for your attention.
Thank you very much, Manfred, for a wonderful presentation that both revisited some of the issues that Art started to address in his presentation, but also adding some other perspectives as well. I think all of this indicates how challenging is, how we are perhaps too enthusiastic in thinking that the big data environment is going to solve all our problems that we need to be solving. There are still huge challenges. So we have, and again, also thank you for, like the previous speaker, being immaculate in your use of time. So we do have another 5 minutes for discussion of this presentation as well. So I open the floor again to comments and questions. Peter.
Thank you, Manfred, for a very nice systematic overview. Could you speculate a little bit further on new types of information which gradually also become very popular? Data are well, numerical representations. But of course we have qualitative, textual, semantic type of information, which gradually also is going to be analyzed through data analytic methods. So on the textual side, would you see some new and different perspectives? And gradually, of course, we see visual information, cameras, sensors, etc., which is another source of information. Would you speculate that perhaps the caveats which you have mentioned for big data analysis would also apply for semantic and textual information, or for maybe in the future visual information?
Most of the challenges I discussed or mentioned relate to all kinds of data inputs, and they become especially severe because of the heterogeneity of data inputs, meaning that the data are coming from very, very different sources. They are unstructured. And if the data are binary, so there are still many challenges, but it is not so difficult to manage. If you have video data and they are in real time especially, then the things are becoming much more complicated. In order to integrate the different data sources, which is a very, very tricky one, for some parts there are some solutions, but it is very difficult to integrate all together. The Hadoop system, for example, provides to a certain extent some possibilities in order to deal with such issues to a certain extent.
If I just may, Jacques, you see, this meeting here is streamed all over the world. So today, all over the world, they can have been watching you and what you have said, and they have seen you. Would it be possible, rather than having an enlightened academic discussion of the final conclusions of a meeting like this, that at the end a very smart information data analytical expert would say, well, we have algorithms through which immediately we can summarize all the findings of what has been said, what has been seen today?
Difficult, extremely difficult.
Okay. If I may, okay, no, please go ahead. And I would like to add some to this discussion. We'll continue in a moment.
I just wanted to pick up on one point that you touched on, which was the idea of crowdsourcing, using crowdsourcing for data gathering. And I'm wondering to what extent you think that might be a strategy to use crowdsourcing as a way to improve the quality of data. You know, we see the example of Wikipedia, for example, getting better and better, more useful to more people. Is that a lesson for us in some ways about how we might be able to use some of these methods to get better quality, more useful data, especially when you're involving the public and public issues?
Crowdsourcing certainly has a great potential, not only in developing countries where less data are available. YASA, for example, is using it in land use management by means of photos which are provided by the people. But also it is very, very interesting in the context mentioned by you concerning noise. Noise monitoring in a city is being used. But what is extremely important is to be careful about the biases which come in, especially if you integrate it into models and then the error will propagate further and further, and you do not know how meaningful the result will be, or is it only artificial? If you are only interested in monitoring noise, then it is fine, of course. You still have problems in this respect, because this is a perceptual view and bias.
Adding to the point that Peter raised, the new sources of information which we may expect in the city. What about the Internet of Things? related to
Now,
the
of
self-driving
course-
cars, the
of course
interaction
it's-
between cars and
Of
infrastructure.
course, it's extremely important to take into account also Internet of Things, especially in the context of smart cities.
Robots.
Because you can link it to electricity and all kinds. This is necessary to do from a technological point of view.
But those new sources of information, I think, underpin what you have said about the complications which we have to... Thank you.
Okay, I'll just take that. Okay, well, if I may, as chair, also ask a question, Manfred. I think this is a really interesting discussion. I'd like to return to the issue that I also started to raise this morning, which is about the representativeness of the research. And, if we start with the viewpoint that all people are created equal and have equal rights, but there's traditionally when we have, say, we used to have census, so we might take a sample and then say, okay, we want this to be representative. So which always means if you take samples, you start taking weighting. Yeah. So but the moment you introduce weights, you can either use statistical techniques on deciding what should these weights be, or you can become subjective, also taking into account maybe issues of quality, different sources. What do we know about weighting of different sources of big data, and how is it? What kind of developments are there to make sure that we are representative of the people that we are actually thinking about?
But the question you raised is difficult as such, but more difficult in the context of big data because we have sub-collections which use different sampling criteria, and you do not know about it, and then you have no knowledge about the whole system. This is the problem. Generally, according to my knowledge, if you do not have knowledge about these issues, then it's equal weighting, the way to do it. And if you have a priori information about empirical, then you can make weighting, but you should be aware that is influencing your results.
So there's also a Bayesian school in the big data analysis? Okay, right. Okay, very interesting. Thank you. Well, I think we have to leave the discussion of Manfred's paper at this point, and then we'll move on to next. But let's thank Manfred in the usual way again for your presentation. Thank you.